Hello and welcome back to another episode of Math with Son. Today we're going to be talking about orbital motion, and we're going to be talking about how orbital motion and centripetal forces must be kind of like equal in terms of gravitational forces. And we're also going to figure out what is the period of the orbit of a moon and why and how fast the moon is going and all of that stuff. So it's going to be kind of a cool episode. So for starters, I want to draw this idea. Let's draw Earth here. There's a nice pretty Earth. All right, and if we have an object spinning around it, like the moon, when the moon is spinning around, if you think about like all objects in general that are spinning around something, they're essentially being held by a string, and that string is being like essentially pulling them inward. So in this case, that string is gravity. All right, when you think about like you twirling a tennis ball, if that tennis ball was going around, you would be holding a string right here, having a great time with that tennis ball. All right, it's the string forcing the ball to go in a circle and spinning it around. It's gravity that is acting as the string. So I'm trying to make connections between centripetal force and gravity because the centripetal force is the gravity of the object. So what is centripetal force? Well, we learned last episode, or at least remembered last episode, that centripetal acceleration is equal to v squared divided by r, and force is mass times acceleration, so centripetal force will equal mv squared over r. And we just said that centripetal force is going to have to match gravity or gravitational force. So if that is equal to gravity, or the force of gravity, then that would equal big G times the mass of your object, which is the moon, and we're actually going to include the mass of the moon in this case, divided by r squared. All right. In other cases, you may have seen me not include the mass of the object, and that's because the mass of the object was you or me or even a car or a space station. Those are nothing compared to the mass of planets, so we just kind of sometimes ignore them. But in this case, we're talking about the moon here, and the moon has a big enough mass that you should probably consider it. You're going to be disappointed, though, immediately after me saying that, because we have the mass of the moon, velocity squared of the moon, divided by the radius of the moon. We'll have to equal, it's the radius of like how far away it is from Earth, not the radius of the moon, would equal big G, mass of the Earth, mass of the moon, we'll call this mass of moon as well, divided by the radius squared. Well, if we're solving for this, we want to figure out essentially calculate the velocity of the moon. So let's solve for the v squared here. So we would multiply by r. If we multiply by r over here, the r's would cancel, and one of those squareds would go away. If we divide by the mass of the moon would cancel too, which is kind of sad, leaving us with v squared is equal to gravitational constant, mass of Earth, the moons cancel when we divide by that, over r. All right, which means the velocity of the moon would equal the square root of gravitational constant, mass of Earth, divided by the radius between the Earth and the moon. All right, well, what does that equal? Well, what is the gravitational constant? Gravitational constant is 6.67 times 10 to the negative 11th. That's a lot. And then times the mass of the moon, which is, not the mass of the moon, mass of Earth, which is 5.97 times 10 to the, 10 to the, what is that, 34th, I believe? It's really big, and it's really blurry on my paper. Sorry. Divided by the distance between the moon and Earth, which is 3.85 times 10 to the 5th. The 3.85 times 10 to the 5th is the few things that would not probably be provided to you on a formula sheet. The mass of the Earth would probably be provided. The mass of gravitational constant you would hope would be provided as well. You can square root all of that and do all the math and calculations, and you would find out that the moon is roughly traveling at 1,008 meters per second. Whew, that is a very fast-moving object. All right, 1,008 meters per second is about 500 miles an hour, I think. No, yeah. Hard to think of. That's big numbers. Our brains weren't designed to think of those big of numbers. Find the period of the moon's orbit. Well, the period of the moon's orbit is going to be dictated by essentially how long it takes for it to spin or do one cycle. Well, if we're going at 1,008 meters per second, and a period would be a one singular rotation, which would be 2 pi r, a circle, we would have 2 pi r divided by the velocity to figure out how long it would take it to go in one complete cycle. So we know the radius. We also know the velocity. If we plug those in to do 2 pi times the radius, that was the 3.85 times 10 to the 5th power, divided by the velocity of 1,008, it would take approximately 2.4 times 10 to the 6 seconds. That is a lot of seconds. And 2.4 times 10 to the 6 seconds, if you calculate it into days, you could multiply 2.4 times 1 out of 1 hour is 3,600 seconds. And then you could multiply by 1 day for 24 hours. And if you do that, you get a roughly, out of room, 28 days, which makes sense because the moon orbits the sun about once every 28 days. Now, you may be noticing a little bit of a hole in some of what I've been talking about, and that is that you may have heard that planets, as well as moons and things like that, they don't orbit in an exact circle. So technically what we did there was wrong. For planets. It's not necessarily wrong for everything, but in general, objects orbit in an elliptical pattern, which is not a perfect circle, and that means that we're estimating here. This is AP Physics 1, people. We're not doing anything like crazy astrophysics here. We're just getting an idea and trying to connect some of the basic laws of physics to something that is not necessarily perfect, but we're not going to correct it either. But Kepler's first law indicates that everything kind of in orbit is more of an elliptical pattern, and it is not necessarily a perfect circular pattern, and they will have a foci between the two things. All right? Don't want to get into that. That's not what this whole channel is going to be about. I don't want to make things more complicated than they need to be, but I did want to address that it's not perfect. Okay? That's going to do it for this one. Until next time, stay positive, my friends. Bye.